are a few questions now. Should we go over them at the end of the class? Are about some specific examples, maybe from last time.
For the examples from last time, right, we can't unfortunately spend today's class doing more 6.5 and 9.3. We really owe it to ourselves to see some of the 6.6 problems that I've prepared for us. This kitten stepping on the keyboard. If you guys came perfectly on time, we have Foster's, and this one's especially is vocal and annoying. But yeah, so we really ought to continue with 6.6. Maybe let me do a quick overview of the pre-class notes really fast, and then I'll open it up to questions and just see kind of what's out there. So yeah, this is we're again dotting some I's, crossing some T's and stuff that really we did in Calculus 1. We just didn't have time for in a one semester schedule. And one of the things that you could have developed back then, we just again didn't have the time, is what are derivatives for the inverse trig functions, right? We already know the derivative of sine is cosine, the derivative of cosine is negative sine, the derivative of tangent and secant and all this sort of stuff. But we can also derive the equations for the derivatives of inverse trig functions. And by and large, the way that you do this is through implicit differentiation. So you can use some implicit differentiation, and then using like a little triangle or whatnot, you can figure out how this relates back to your original variable x. And that's one way that you can come up with all of these equations here. Just as kind of a side note, right? So this is kind of getting fairly heavy into the trig stuff with the domains and ranges and whatnot. And similar to the logs and the exponentials, maybe you'll have a few problems related to the the more algebra side of stuff. But of course, in our class, we're going to be most interested in the calculus, right? How do you actually do calculus with these things? What are the derivatives, the antiderivatives, all that sort of stuff. One thing in particular that I know comes up every semester is our textbook's choice for the domain, the restriction domain for secant in order to create secant inverse. If you're writing an algebra textbook or whatnot, and unfortunately, like if you go and you Google on many websites, things like Wolfram Alpha even, or I'm not sure how detailed the page is for like on Wikipedia, they may choose a different restriction domain for secant, which of course becomes the range for secant inverse, for their choice. And so they may, instead of going for this one here that our textbook comes up with, 0 to 2 pi and then pi to 3 pi over 2, a lot of them do 0 to pi over 2 and then pi over 2 to pi. And you can do this, but then the derivative equation, and again, we are a calculus class, we're most interested in the calculus, the derivative equation becomes more complicated. So if you choose that different domain restriction for secant, then you would need an absolute value, because actually on this other piece, this pi over 2 to pi, this is off by a bit. And so the way that Stewart, right, the author of our textbook, decides to restrict secant is by choosing this other kind of leg of secant from pi to 3 pi over 2. You don't need the absolute value, and so the derivative becomes a lot simpler. And so just as a heads up, you'll see a Weber problem or two where kind of you have to, and there's a hint and everything below it, but I've seen it come up on Piazza already this semester as far as just making sure you have the correct domain restriction for secant in order to create your secant inverse. This right here table is given on the exam formula sheet. And so as far as the exam, and there's a lot of stuff to remember, right? These you don't have to have memorized completely. As far as the quizzes go, right? So of course, our upcoming quiz on tomorrow, Tuesday, does not cover today's material, right? It covers the last week's stuff. So 6.2, 6.3, 6.4, 6.5, and a little bit of 9.3, right? The separable differential equations. Those are the topics for tomorrow's quiz. But in the following week's quiz, right, really, I think these are kind of the standard 3 that you should have memorized as far as quizzes go. So, and really out of these 2, you need to have, these are the big ones. You should know the derivative of tangent inverse, and you should know the derivative of sine inverse, right? And of course, from here, you can see sine inverse and cosine inverse are very, very similar to one another. It's just the cosine inverse has a negative. So, right, there's certainly some connections that can be made here. And so those are the ones that you're really expected to have memorized for a quiz. All right. From there, right, we do a fair amount of problems related to that. And that's kind of where we're going to pick up in today's class, right? We have 2 pages worth of derivatives and 2 pages worth of antiderivatives, things that we'll be using this information about derivatives of inverse trig functions. All right, with that, let's go ahead and open it up to a few questions. What are you seeing on the Q&A, Luis? You're muted, by the way.
Yes. So I'm getting mostly not math related questions.
Okay.
More administrative stuff. There's no math right now.
Okay. Fair enough. Well, with that, let's go ahead and transition then. Oops. I don't know why my... oh, there it is. Apple Pencil wasn't working for some reason. Let's get into the problems for today. So again, about inverse trig functions, we have a few that are just, hey, find the derivative of stuff. So again, you kind of have to have the derivative formulas memorized, for sine inverse and for tangent inverse at very least. I expect also probably cosine inverse. But here's an example problem. So find the derivative of this. It's nice. It tells you exactly what to do. No hidden wording or anything like this. And so let's go ahead and take the derivative. So again, when we go and we take the derivative of sine inverse, this is one of these that you should have memorized. It's 1 over the square root of 1 minus x squared. And then for this second bit here, this is, well, a product of 2 functions, right? Even though it doesn't have the multiplication symbol there, we know that this is kind of optional to write it or not, that this is a product of 2 functions in terms of x. So when we go to take the derivative of this, we have to use the product rule. So the product rule goes the derivative of the first times the second plus the first times the derivative of the second. And okay, well, this is a bit complicated, right? So the derivative of the second, this square root of 1 minus x squared, right? This is a composition of functions. There is a function inside of another function, right? The outermost function is the square root function. And then inside of that, there's something more complicated. And so anytime you go to take the derivative of a composition, right, we have to use the chain rule. So here, mid-product rule, we are now switching and thinking about the chain rule when we go to take the derivative of the second function here. So again, square root is the same thing as 1/2. So we're going to do bring the power down and reduce our power by 1. So the 1/2 comes down, we go to negative 1/2. The chain rule says we should leave the inside alone. So we took the derivative of the outside function, the square root, leaving the inside alone. Then we come and we multiply by the derivative of the inside. So on the inside of the square root, there's this 1 minus x squared. The derivative of that is negative 2x. So this right here, all of that is the derivative of the second, right? The derivative of the square root of 1 minus x squared. Right here, this is something that, WebWork would accept. You could type this all out and, it would work out perfectly fine. We can simplify a little bit. Of course, in D2L, if this was maybe like a multiple choice style question or whatnot, maybe it does simplify a little bit for us. Or maybe it has you, right, if this was a D2L question and it's one of these where you have to input a number, maybe it asks you for y prime at, x equals 1/2 or x equals 1 or something like that. In which case, right, you would just take this and plug it into your calculator a little bit and, see what the answer is. So let's see, the 2 and the 1/2 cancel there. We have 2 x's and a negative. So I'm going to make that negative there. The x's are being multiplied together. And so x times x is x squared. And then the only piece that's left is this right here. This has a negative exponent. So that means it's in the denominator and it's 1/2. So this is square root. So the negative 1/2, again, in the denominator because of the negative and a square root because of the 1/2. So if you'd like to, right, you could continue to simplify this down. I'm going to go ahead and leave this as is. In fact, if you do simplify it down, it does make it's a pretty nice final answer actually. But if you have to get common denominators and all that sort of stuff, but here's where I'll probably stop. All right, questions about this specifically? What's coming up in chat, Luis?
So about this, someone's confused about the 1/2.
Okay. Yeah, the 1/2 is, I did kind of skip a step there. Really what we would do is do a rewrite, right? So this right here, the square root means 1 minus x squared raised to the 1/2. So again, that's a way to rewrite square roots in their exponential form. And then when you go to take the derivative of this, hopefully this follows a little bit more closely or obviously here, right? The 1/2 comes down, right? We're using the power rule at this point. So excellent. Anything else coming up?
So this is a bit more general, but someone is confused about how the domains for example, inverse trigonometric functions affect derivatives and integral, if they do.
Yeah, so for instance, what I was talking about for like secant inverse, so this is going to be a bit on the side here, right? When we talk about secant, for instance, right, secant looks like this. Remember, secant is 1 over cosine, so it's going to look something like this. And then when you plug in 0, when you plug in pi over 2, cosine is 0. So when you're dividing by 0, that's an issue, right? And you have an asymptote here. And then you go something like this. Let me draw these out. And then again, at 3 pi over 2, you have an asymptote, someplace where cosine is 0. And this just kind of continues on. And right, when you go to find the inverse function, remember inverse functions back in our algebra days, right? They needed to pass the horizontal line test, right? And so this function right here does not pass the horizontal line test. So as it sits, it does not have an inverse function. And so what you do, and what we've always done, is that we restrict down the domain in order to create an inverse function, something that does pass the horizontal line test. And so one way that you can restrict down the domain is that, well, we're going to delete, right? Notice that maybe along the top here, this doesn't pass the horizontal line test. And so we're going to delete a lot of it. So I'm going to delete maybe all of this, and I'm going to delete the left half here. So all that is left is this restriction from 0 to pi over 2, this piece right here. And then in the bottom, right, the bottom doesn't pass the horizontal line test either. And so we're going to delete all of it here, except for maybe one piece. And so if you choose this piece right here, which a lot of algebra textbooks do, and some online websites as well, then certainly it passes the horizontal line test, which is great. But in comparison, right, and notice, so this is related, we need to talk about derivatives or the slopes, right? The derivative here is going to be different than if you delete that and instead leave this piece, which is what our textbook does, right? And so if by leaving this piece here, right, the slope is going to be different. And so that's kind of how these things are influenced by what restrictions you choose on the domain of your inverse trig functions in comparison to, right, to the derivative formulas. So it is fairly complicated, but right, if you follow our textbook's convention and everything, the derivative formula is quite nice. I see there's a student with their hand raised, so let's go ahead and hear from them. Josh, you're up if you have a question.
Oh, sorry, I still had my hand raised from earlier. My bad.
Oh, okay. Yep, no problem. All right, so let's do another problem here. Find the derivative of this, right? So again, kind of some nice wording. It's hopefully clear what to do. The derivative of tangent inverse is going to be 1 over 1 plus x squared, but in this case, our variable is t, so we'll use t squared, I suppose. And then for the second bit, we're going to need to use the quotient rule, right? Because we have a quotient of two functions. So it goes, right, the derivative of the top times the bottom minus the top times the derivative of the bottom, all divided by the bottom squared. And so again, we can maybe spend one line simplifying. I'm not going to go too crazy with this, but let's see. 1 times anything is itself. And let's see, we have a 2 and a couple of t's. So let's see, t squared minus 2t squared. So this is going to be, looks like we have -1 altogether, right? We can combine like terms. We had 1 positive and 2 negatives. So altogether, we still have 1 negative remaining there. And then 1 plus t squared quantity squared. So this right here, again, would be a perfectly reasonable spot to stop and insert this into WebWork. If this was a D2L quiz or an exam, right, where you had a number answer, right, maybe you plug in t equals 5 or something like that, right? You could go ahead and just plug that in, and that would give you the slope of this curve at x equals 5. Okay, let's see. Let me do this problem here, and then we'll open it up for questions just because I am a little bit worried about our time here. Find any relative extrema for this function. So this, again, is going to be a derivative question. However, this wording here is a little bit maybe more confusing, right? This is an application of derivatives. This is something that we brought up back in our Calc 1 days. Right? How to find relative extrema, that is minimums and maximums, relative minimums, relative maximums for this function right here. And so the thing that we have to remember back from our Calc 1 days is that if you want mins or maxes, you need to be very interested, right, in critical points. Critical points house all the potential minimums, all the potential maximums. And critical points are right where our derivative is 0 or undefined. And so the first thing that we need to do is take the derivative and figure out when it's 0 or undefined, because this lists all of our potential mins and maxes. So let's go ahead and take the derivative of this. So when we take the derivative, well, the derivative of sine inverse is going to be 1 over the square root of 1 minus x squared. And when we take the derivative of negative 2x, we get negative 2. All right, so the question is, where is this undefined and where is this 0? And so while we could talk a little bit about when it's undefined, you know, when x is equal to -1 or 1, right? So if you plug in -1 or 1, notice that you're dividing by 0. This came up quite often in our Calculus 1 days. But remember, kind of -1 and 1 is just on the outskirts. It's the very endpoints of the domain of this function anyway, right? And so because these are endpoints, we'll already have to take those into consideration one way or another when we go and we evaluate at the very end. So we're going to be using kind of we could use the closed interval method for this. All right, so that's when it's undefined. When it's equal to 0, this is kind of the classic. This is what everyone did, right? You take this and you set it equal to 0. And we can find some other points here. So now we're in algebra mode, right? We did our derivatives. Now we need to solve this algebraic equation. So we'll go ahead and do a little bit of rearranging. So I'll add 2 to both sides. Maybe we say that we don't like fractions. So let's get rid of the fractions here. So I'm going to multiply through by this square root of 1 minus x squared on both sides. We need to get rid of the square root, right? We're trying to solve x equals. So I need to get rid of the square root here. So let's go ahead and square both sides. So I'm going to square this side and square this side. Of course, when I square 1, that's fairly nice. It's just 1. When I square the left-hand side, we get a 4, and the square and the square root will perfectly cancel out, which is kind of what I wanted. Again, my quest here is to solve for x. So to that end, why don't we go ahead and trying to get it by itself, we can divide by 4. Then we can do a little bit of rearranging. Maybe I'll bring the x squared over here, and 1 minus a fourth is 3/4. Then we can go ahead and take the square root on both sides, and we get plus or minus the square root of 3/2. So those right there are some critical points. So now what we did, right, when we wanted to find relative extrema, is that we'd go ahead and plot them on a number line, right? So these are our critical points, maybe negative √3/2 and positive √3/2. And remember, this function doesn't go on forever, right? It has a restriction. It doesn't make sense to, for instance, to plug in 2 or 3 or 5 into sine inverse, right? Sine inverse only makes sense if you plug in things between -1 and 1. So that's why I said, right, these were the endpoints of the domain for sine inverse. So this is kind of our restricted number line dealing with sine inverse. Now we can go ahead and choose some test points and plug these in here, right? So for instance, if I choose 0 in the middle here, that's between negative √3/2 and positive √3/2. These ones, it's maybe a little bit more difficult, right? We can use maybe our TI-30 calculators or whatnot. And, something that's bigger than √3/2 turns out, right? And again, you can plug this into your TI-30 calculator and see what a decimal approximation would be for that. But you could do something like 0.9 or -0.9, right? So these right here would be our test points. So now we can take those and plug them into our derivative function. So again, here's our derivative function. And we're interested in when is it increasing and when is it decreasing, right? Because that will tell us whether we have local mins or local maxes. So for instance, if I go ahead and I plug in 0 into our derivative function, right? So again, this is all about the derivative because that's telling us if we're increasing or decreasing or not. So if I plug in 0 into this, so just off to the side here a little bit, f prime of 0. Well, I get 1 divided by √1 minus 2. So this right here, again, we can plug it into our calculator, or you can do just a little bit of simplifying right here, and you can see that this ends up being negative. Okay, what about if you choose something like 0.9? Well, this is a little bit more complicated, but again, we have a calculator. So if I choose something like 0.9 and I plug this in, so I get 1 divided by, and actually, so I don't have to switch back and forth between my screens and whatnot. Maybe Luis, can you help me out with this? So if I do 1 minus 0.9 squared, I take the square root of that, and if I subtract away 2, I'm sure this will take you 30 seconds or so to.
I see.
What does this end up equaling? Someone beat you.
I'm getting 3.26.
326. I got in chat 0.29. You said 0.326. I'll trust you for the time being. But yeah, either way, hopefully everyone agrees that it's a positive. Now I have 3 people outvoting you. I'm sorry. I'll take their word for it for the time being.
Yeah, you should trust them.
But yeah, so you plug this into your calculator carefully, right? And either way, you see that you get a positive number, right? That I know for sure. And likewise, if you plug in -0.9, right, the fact that you're squaring it, right, will turn out that, this is the exact same result and you get a positive number here. So this means on this interval, it was increasing and then we have decreasing, right? Our derivative was positive, then our derivative became negative. That means that at this point right here, we have a local maximum. So x equals -√3/2 is local max. And likewise, at x equals √3/2, we had that it was decreasing and now it's increasing. This is going to be a local min. Oops. So again, these are the relative extrema for this function right here. X equals -√3/2. This one's the max, and √3/2, that one's the minimum. All right, so with that, why don't we go ahead and pause? There's a couple questions, a couple problems, examples 2 and 3 here. Let's maybe first I'll allow a few folks to talk. Will, we haven't heard from you today. Will, what question do you have for us?
So I'm just trying to figure out what do we use the x equals -1 and 1 for?
Yeah, great. So technically, in the definition of critical points, these are critical points, right? So critical points are where your derivative is either undefined or 0. The problem is, though, is that these are endpoints, and endpoints can't be local mins or maxes, so they're not relative extrema. And so it's getting into the, I don't know, the subtleties of all of these definitions. So the big
normally they would be endpoints, or normally they would be, wait, sorry, I'm confused.
No, yeah, they're endpoints of the domain of this function. Endpoints
of any sine function?
Of the sine inverse function, yes, exactly.
Right.
And but endpoints cannot be local mins or maxes according to the definition in our book. So that's why we really don't do anything with them.
Okay, thank you.
Yeah, definitely. All right, and Jeff, I'll allow you to talk here. So yeah, what's up?
Thank you, Professor. I had a quick question as far as, are we going to be expected to remember the domains of the inverse functions as well as the inverse functions?
I would say that for our quizzes and exams and whatnot, we try not to make this a focal point of the, these things. And so, yeah, we're not going to test it so heavily.
Okay, thank you.
Yeah. It's one of these things where you could get, a fair amount of partial credit or whatnot. If we did have something like this problem here, it does kind of rely on that a little bit. But yeah, so you could still get a fair amount of partial credit by, taking the derivative and setting it equal to 0 and kind of forgetting about some of this domain issue stuff. What's going on in the Q&A, Luis?
So one question is relative extrema a different word from local min and max?
It's the combination of the two. So relative extrema is just another way to say local mins or maxes. Those together make up relative extrema.
Right. It means the same thing.
Exactly. Yes.
Then I have questions about other exercises. Well, one question that I don't
anything
really
from
understand.
example 2?
Yeah. So one from example 2 was how did the 2t squared disappear?
Yeah. So the 2t squared, notice here that there are like terms. So we have the 2t squared here, and we have the 1t squared here, right? But that 1t squared is positive, and the 2t squared is negative there. And so they actually combine and they make a negative t squared. And let's go ahead and call on Jakayla. Jakayla, you're up.
Okay, I had a quick question from the first example.
Yes.
Okay, I just got a little lost. I understood the chain rule and the first part of it, but I got lost where the x came in, the plus x. Where did that come from?
The plus x right here. So this came from the product rule. So when we did the product rule, we needed to do the derivative of the first. So the derivative of x was 1 times the second plus the first times the derivative of the second.
Okay, I see.
Excellent.
Thank you.
Of course. All right. Well, let's get into some of our anti-derivative stuff, right? So we've done lots so far about derivatives. Let's go ahead and see these from another light, right? The anti-derivative stuff. So here.
Before starting this exercise, someone asked if you could solve 6.6.12. Is that possible?
6.6.12.
Does that exist?
Like this? I mean, we solved it in the pre-class videos.
I see. Right. So someone's confused about that, but maybe they can ask that in an office hour.
Yeah, office hours or Piazza or whatnot. Right. I'd be happy to elaborate, or even after class. I'd be happy to get into this a bit more. So, all right, here we would like to integrate cosine divided by 1 plus sine squared. And again, this is a quite complicated integral. And remember, I've told you guys now multiple occasions, right? Whenever you have a complicated integral, our only really technique right now that we have, is u substitution, right? So we're going to try u substitution. And so I think maybe the first thing that I would probably try on this, right, is u equals, and quite often the denominator has worked out well, right? So the 1 plus sine of x. But sadly, if you try this out, so du is equal to sine x times cosine x, right? So you need to use the chain rule here because you have sine of x squared dx. And you kind of continue on and you try to solve this. Let's at least set up the integral here. So this would be the integral of cosine of x divided by u. And instead of dx, right, we're going to write du divided by 2 sine x cosine x. You can see that the cosines kind of cancel, but right, you still have some x's left over, right? We haven't been able to successfully transform from x's all into u's. And so this is an indicator, right, that maybe you're headed down the wrong path. So unfortunately, I mean, we could continue to try to push in this way, but it gets even kind of nastier. And so it turns out there is a better way, right, to do this one. And again, with U substitution, right, you just kind of, you try things, especially for these first couple problems where maybe you haven't seen so many examples of kind of what can be done now. So we tried this, it just didn't seem to work. So we're going to try something else, right? So instead of maybe the entire denominator, let's choose another inside function. So in particular, I see sine is inside of the squaring function. So I'm going to try u is equal to sine of x. And this will work out, turns out a lot better because its derivative, right, du equals cosine of x dx, you see its entire derivative is hanging around in the problem there, right? The problem with choosing maybe this du is that, you know, we didn't have this 2 sine x cosine x hanging around here. And so we got a little bit stuck, right? There was nothing to really cancel with the sine that came out. And so we don't have this problem if we just choose u equals sine of x. So let's go ahead and kind of start to transform this now. So let's see, I'm going to have cosine of x on top. I'm going to have 1 plus u squared in the denominator. And remember, let's see, my dx in this case is the same thing as du over cosine of x. All right, so when you go ahead and you solve this for dx, you just have to divide by the cosine. So now you can see that the cosines perfectly cancel, and we were able to successfully transform this from all x's to all u's. Moreover, right, of course, you know, being that we're studying here 6-6, the stuff with the trig inverses, probably this looks quite familiar, right? This is supposed to be this whole tangent inverse stuff. The trick certainly is remembering that when it comes to the quizzes and the exams, things like this, right, where you have kind of multiple sections that, hey, we've seen this before, we know what to do with this. This is going to be tangent inverse of u plus a constant of integration here. And so now we can go ahead and plug in, maybe instead of u, we can go ahead and put sine of x plus my constant of integration. In the interest of time, this is probably where I'm going to leave this one. You can simplify it using some trig stuff, right? Making a triangle and everything and relating together these angles, and, you know, trig functions and inverse trig functions can always cancel. If we have time, I'll come back to this. But for the time being, this is where I want to leave it. And I want to make sure that we can talk about both of these other problems as well. Maybe we can take one quick question if we have one out in the Q&A.
We don't have any math question.
Okay. Great. Let's go ahead and continue on to B here.
Well, actually, there is a question, a general question.
Okay.
Can tan inverse be written as sine inverse divided by cosine inverse?
This is a great question, right? So can tangent inverse be written as sine inverse divided by cosine inverse? And probably you can tell by my choice of pen color that sadly, this is not true. In particular, right, the domains are quite significantly different. Tangent inverse here makes sense across all real numbers, while sine inverse and cosine inverse have restrictions, right? Sine inverse and cosine inverse only exist between -1 and 1. So that's one maybe quick way to convince yourself that this would not be equal. But also, I mean, anytime you have a fun question like this, right, we have calculators and you can go ahead and test these things, right? So you could plug in, you know, x equals 2, you know, to the left-hand side and to the right-hand side, and you'll see that you get these different outcomes. Excellent. So with that, let's go ahead and tackle B. So this is another one kind of quite complicated here. Thinking about that, we are here in 6.6, right? We have to think about what maybe trig inverse function this is most similar to. So I remember we have stuff about maybe sine inverse, cosine inverse, tangent inverse, secant inverse, all these sorts of deal. And I think that, you know, a lot of these have square roots in them. So you notice that this doesn't have any square roots. The only one really without square roots that that we should certainly have memorized is, for tangent inverse, the one that we just did here. So if you do the inverse, the antiderivative or the integral of 1 divided by 1 plus x squared dx, this is equal to tangent inverse of x. Of course, sometimes I like to write this with u's here, just to really emphasize that you can do this with more complicated things. So we're going to try to make what we are given, right, the problem that we're asked to solve, look like this right here, because this is something that we know how to solve. So we have to manipulate what we have here, right, in order to hopefully make this into 1 plus some perfect square, if at all possible. And remember, we did see this in class, in the pre-class videos, right? It doesn't necessarily have to be a 1 here, right? If this was like a 4 or really even like a 3 or anything like this, that would also be fine. But a constant plus a perfect square is the key here. So the question is, how can we rewrite this in this good format? And so we need to kind of revert back to our algebra knowledge, right? This is how we kind of rewrite things, and write down equivalent statements is from our algebra days. Does anyone happen to remember, and you can type it in chat or in the Q&A, a technique that would allow us to rewrite this so that we have a nice squared bit? Yeah, I see it here in the chat, and I see, people with answers and the technique and everything in the Q&A. Excellent work, guys. Yeah, so the answer is completing the square. So this, was maybe your algebra teacher's, one of the ways to torture you to some extent, but there's a reason why, right? There's a reason why you learn these techniques. And that is sometimes in calculus and whatnot, when you go to find an antiderivative or derivative, right, you need to be able to write stuff in an alternate format, right? This, we don't know what the integral is, but if we complete the square, the claim is we can get some result here. And so remember, for completing the square, you need to look at the thing that's next to the x, right? This was your b value. So in this case, -4. And so let me go ahead and kind of pull off to the side here. If we have this -4, in order to make this a completed square, the thing that we needed to add here was you take your b value, you divide it by 2, and you square it. That was the right thing in order to turn it into a perfect square. So in this case, -4 divided by 2 would be -2, and we square that and we get 4. And so this right here is a completed square. If you go ahead and factor this, you will see that it's x minus 2 times x minus 2. So x minus 2 quantity squared. Now we already have a constant. Oops, it's the eraser there. I meant to use the highlighter. We already have a constant, right? This is not just x squared minus 4x. We have this plus 5. And so we can go ahead and break up that constant, x squared minus 4x plus 4, plus an extra 1. This right here is a perfect square. We just need to put it in the correct format. So let's go ahead and rewrite this. So 1 divided by, and this is the same thing as x minus 2 quantity squared plus 1. So I've rewritten this in a perfect square format, right? And so now we can see, well, we have something quantity squared. This would be an excellent choice for a u, right? We were trying to figure out maybe how can we rewrite this? And I think now using a u substitution would be excellent. And so if I use u is equal to x minus 2, notice we have a very nice du. It's just equal to 1 dx. And so we can go ahead and exchange. This is going to be the integral of 1 divided by u squared plus 1 du. Exactly the format that we need, right? This is exactly tangent inverse. So tangent inverse of u. U was something recreated. It was x minus 2 plus a constant of integration. So this right here would be the final answer. Again, if this was a web work problem, you could type this in. If this was a D2L quiz or an exam problem, right, we can make this a multiple choice. You have to select it. Or of course, we could ask you to evaluate out a definite integral and give you some bounds, right, from 0 to 1 or something like that.
So one question is if there's like a general formula for completing a square.
There is. So if you have at least something like x squared plus bx, the correct thing to add to this in order to make it a perfect square is going to be b divided by 2 quantity squared. So that's why we took our -4, we divided it by 2, and we squared it. And that's what made it into a perfect square. So if you have this, then this is going to be the same thing as x plus b over 2 quantity squared. And you can double check. If you expand this all out, right, you FOIL it, the first, the inners, the outers, the lasts, you'll get exactly this. So that's where the formula comes from. That's why it is the right thing to add, sort of deal. Okay, I see there's some folks with their hands raised. Let's go ahead and call on a couple people. Alec, you haven't asked any questions today. What's up?
Just for my sake, right before you integrate, you have u squared plus 1. Say that's like, you said it could be any constant, like +2, for example. Where does that end up when you integrate, like with the inverse?
Yeah, so you would have to do some rearranging, a bit more algebra, and probably another substitution is what I would recommend. This comes down to like what we did for this example right here, right? So if you had, it'll certainly be easier if you have a perfect square. But if you did have something like 1 over x squared plus 2, you could rewrite that as the square root of 2 squared. Right. So then your a value here would be the square root of 2. And you can see in the final result how this would appear, right? You would have 1 divided by the square root of 2, tangent inverse of this u divided by square root of 2 plus your constant of integration.
All right. Thank you.
So yeah, it's a bit complicated.
Yeah.
I would, as the final answer to that. It's complicated, it's doable, but I'm not sure if that's the best use of, time as far as, we have quite limited quiz and exam time. And so
I gotcha.
It may not be worth it to ask such a algebraically complicated thing.
All right.
All right. Let's see. Jenna, you haven't asked any questions today. What's up?
Can you hear me?
Yes, sure can.
So after you finished completing the square and you had x squared minus 4x plus 4, why did you put that additional 1? Was it because in the original equation there was a 5 up there?
Exactly. I didn't originally have +4, and we can't like create or destroy. If we do, then it'll change our answer, right? We're supposed to be getting the answer to this question, not some other made up question that I just, came up with mid, solving this one. So yes, I have to kind of keep it all together. So I can break it apart and I can rewrite 5 as 4 plus 1, but I can't just outright change it to a 4.
Okay, thank you.
Yeah, definitely. All right. So let's do Sam as well. And then I would like to spend a little bit of time just looking at this other example, and then I'll open it up to more questions. But Sam, you got the floor. What's the question?
Oh, so just building on the question before this one, or I mean, actually 2 questions before.
Mm-hmm.
So for instance, if I were asked to take the integral of, say, 1 over the square root of 4 minus x squared.
Yes.
So yeah, actually like the square root of that.
The square root
of the denominator. Yeah, exactly.
Yeah. Mm-hmm.
So that looks like, for instance, like sine.
Yeah.
Inverse sine.
Exactly.
But like,
yes.
I see that I have a 4 instead of a 1. So would that still apply? The fact that it would be like the same answer?
It wouldn't be the exact same. You have to be a little bit careful with this. But yes, you could use the same technique, right? And that is try to create some u substitution, maybe divide by this 4 across the board sort of deal. Notice that 4 is inside of a square root. So you have to, be a little bit careful with that. And when you divide by that in the denominator, you should also divide by that in the numerator. So that way it's just a fancy multiplication by 1. But yes, the exact same strategy we used in the pre-class video problem will apply to this here.
Okay, cool. Thanks.
Yeah, definitely. All right. With that, let me talk a little bit about this problem right here, and then we'll open it up to questions. So I'd like to integrate, and this 4x plus 3 divided by the square root of 1 minus x squared. And oops, there's a typo here. I didn't tell you what we're integrating with respect to, dx. Sorry about that. And so, okay, we can look at this for a little bit. And this one, I think, is maybe a bit challenging to figure out what exactly we want to do with this. I see that in the denominator, right, I see something that reminds me a lot of sine inverse, right? but the numerator is more complicated, right? I have kind of these extra pieces in the numerator, and that right is where the difficulty lies in this. And how do I deal with this more complicated numerator? And so in order to solve this, we're going to use a technique very similar to our last pre-class video problem. And that, remember, with fractions, you can always split these things up, right? And so I'm going to go ahead and rewrite this as 4x divided by the square root of 1 minus x squared plus 3 divided by the square root of 1 minus x squared dx. And now the second bit right here, right, this pretty much lines up exactly with our definition for the derivative of sine inverse. And so, of course, the antiderivative of this is just going to be, well, the 3 is along for the ride, and we get sine inverse of x. The only question that remains really is, how do we deal with this bit right here? Is this sine inverse, or how on earth do we integrate this thing? And so that's the question that I'd like to pose to you all here. And if you would please maybe type it in chat or in the Q&A. How do you integrate this thing? How do you integrate 4x divided by the square root of 1 minus x squared? Yeah. See a lot of good answers. Of course, it's a complicated integral, and so a u sub should be at the forefront of your mind here, that we should use a u sub, and that is true. And so u equals 1 minus x squared turns out to be very good at solving this problem, because you can see the du equals negative 2x dx, right? You can see that kind of hanging around in the problem here. Right? And so that's going to be very useful for when we actually do the u sub. And so yes, a u sub is the correct answer. Good job, everyone. And so, okay, let's do the rewrite here. So we're going to have 4x divided by square root of u. U is going to be my 1 minus x squared. And then if we go ahead and we solve, instead of dx, we're going to be integrating with respect to du. Let me go ahead. I'm going to do dx is equal to du divided by negative 2x. And so this is going to be du divided by negative 2x. We can see that there's some canceling that happens. The x on top and bottom, excellent. We can see there's a 2 that cancels. And so what I'm left with, let's see, we have a 2 left in the numerator. We have a negative in the denominator. Of course, when you divide by negative, this is just going to make the result negative. So I can maybe factor that out or pull it out of my integral. And then this becomes the integral of, let's see, 1 over square root of u. So 1 over square root of u du, and plus, right, we already have this bit done. So when I go to integrate this, again, you have to be very careful. You know that the integral of 1 over something is the natural log. Don't get too natural log happy, right? This is a problem that you did back in your calculus 1 days, right? This is not just 1 over u. This is 1 over the square root of u. And right, so really what you should be doing here is a small rewrite. This is the same thing as u to the negative 1/2 power, right? So the fact that it's in the denominator means that you have a negative exponent, and the fact that it's a square root means that it's a 1/2. And so, okay, when we go ahead and we integrate this, we need to raise our power by 1. So it goes from negative 1/2 to positive 1/2. And then we multiply by the reciprocal of our new power. So the reciprocal of 1/2 is 2. Don't forget, we have this other negative 2 hanging out in front. And all this stuff is behind here.
Should be sine inverse. Someone is pointing out.
Oh, yeah, thank you. You said, when you make the correction like this, in the middle of class, it saves me like 20 emails, right? Because if I post the wrong thing, I hear about it. So I really appreciate, correcting me in class. All right, so final result, negative 4. Instead of u, we're going to put 1 minus x squared. Of course, that 1/2 power means the square root. And here is the final result, I think. Unless I've made another small error. This really comes up, by the way, when you guys are doing your webworks for the next section about hyperbolic trig functions. You'll have stuff like not just sine of x, but you'll have hyperbolic sine of x. and you'll have to type these out in WebWork. And one of the most common mistakes that I see people make is, they forget the H. And so, when the answer is really hyperbolic sine, they type sine. And of course, WebWork just marks this wrong, right? And so, yeah, you have to be very careful about that. So I'm falling for the same thing that I want you guys to avoid, especially next time. So, yeah, I missed another white spot here. I'll zoom way in on it just to upset people, I suppose. All right, with that, thank you guys. It's 2:40. I understand if you have to take off, by all means do so. I'll stick around for a bit here and answer any questions that you guys may have. So maybe first, Luis, Q&A, what's going on?
So regarding this problem, there's a, where did the 2 come from after getting used to the power of 1/2?
Yeah, so this bit right here. So it comes from, remember, I was taking the antiderivative of u to the negative 1/2. So I was applying the power rule for antiderivatives. So maybe one way to see this, if you want to integrate x to the n dx, then you have to raise your power by 1, and then you multiply by the reciprocal of your new power, right? And remember, this is supposed to be an antiderivative. So if you take the derivative of this, you should get back to where you started. So you see, right, the n plus 1 in the exponent slot comes down and it cancels with this. That's why that's needed. And so we applied just this rule, the power rule for antiderivatives, to our u to the negative 1/2. So again, we raised our exponent by 1, and then we multiplied by the reciprocal of our new exponent. And if you take the derivative of this, you will see that you get back to where we started. You get back to u to the negative 1/2. Yeah. Excellent. Any other questions?
So you said u to be 1 minus x squared. Yeah, so someone was asking if the denominator shouldn't just be u, but I guess because of your choice, no.
Yeah, if you just let, yeah, because of the choice, there's still the square root that needs to be accounted for. Remember, a good rule of thumb for u substitution is allowing u to be an inside function. So letting u be inside of the square root, the 1 minus x squared, turns out to work out very well in this case. If you let it be the entire thing, the square root of 1 minus x squared, then your du becomes much more complicated and things don't cancel out so nice. So you'll get stuck.
Some people are worried about the -2 multiplying everything or not.
So the -2 here, let's see, where did this come from? The -2 came from, there was a couple pieces. It was the 2 here and the minus here, right? But these were both parts of just the first bit, right? So this is the 2 came from a little bit of canceling with the 4x, right? It didn't have anything to do with the 3. And then the negative came from our substitution of just that piece, right? From x's to u's, right? Because this is the only one that we required the u substitution for. So yeah, this bit here with the sign and everything doesn't have anything to do with that -2. But it's good to be worried about that for sure.
Always worry.
Oops, yes. Yep, go back and figure out where it came from, and yeah.
Someone's asking if you can use 4x plus 3 as u.
I think that's a wonderful thing to try. I think the denominator will cause you a lot of issues. But it's not obvious, right? And so I think it's certainly worthwhile to see what those issues are. Like trying to transform everything in terms of u's will be a real problem, right? But again, it's not obvious at this point. So you should try it out. You should see what kind of breaks. And that way, if you are on a quiz or an exam and you have to decide what your u is, right? You can kind of see how things typically break and kind of when you should stop and turn around and try something else. And so I think that's a great skill to be developed. Let's go ahead. I'm going to call on a few folks who have raised hands here to ask some questions. So Jeff, you're up first.
Thank you, Professor. I had a quick question. If we were taking a if we were integrating and we had the -1/1 plus x squared and we forgot about the cotangent, would it still be the correct answer if we took -1 times the inverse of tangent?
Absolutely.
Okay,
Yes.
thank you.
Yeah. So if and to similarly for your question, if you had -1 divided by the square root of 1 minus x squared dx, and remember, according to our rules, this is just equal to cosine inverse, but it's also perfectly fine to say that this is equal to the negative of sine inverse. So this is also a true statement. Yep, definitely. And by the WebWork knows this too. And so that's an extra nice thing, is that it will mark both of them correct, so long as you don't have any other underlying issues. But yeah. Okay, let's do another one here. Danny, you're up.
Hey, I just have a quick question. So for the last problem, for example 5,
Yes.
when you're at that -2 times the integral of 1 over square root of u,
Yes.
could you just plug for u, like could you just plug back in 1 minus x squared, and that integral is the sine, the inverse sine of x. Could you just do that and then multiply the -2 afterwards?
Yeah, that should work out.
So would the answer be the same?
So this would be, the problem is though, right? We've already said that we're integrating with respect to u. So if you wanted to instead switch and integrate with respect to x, right? Then you would need to swap out, instead of your du's, your dx's.
Oh, okay.
So yes, it's possible. The problem is, once you swap out that du for dx sort of deal, it wouldn't look like sine inverse anymore.
Yeah, okay, that makes sense. Yeah. Okay, thank you.
Yeah, no problem. Good question. All right, Anito, you're up.
Hi, so I have questions about 9.3 stuff, like general things. So I remember at the end of class on a Friday, we talked about like that plus C constant.
Yes.
So I think my friend explained it to me, because like before, like we had that whole conversation, I swear I had it down, and then after that class, I just got like confused again.
Okay.
But so when we have the plus C, like we integrate both the X and Y sides, right? And then like,
yes,
we do not have to like, because like we have to like solve for the initial value problem, right? So like we don't have to necessarily like solve for like, the Y, like simplify the Y down and whatever, because like all of that, like, let's say it's Y over 2, right? We'd have to multiply the X and the C by 2 and whatnot. So like, can we like, I guess like not do that, like leave the C until the very end rather, or like plug in the initial value, or like, the Y of 0 equals 5, and then plug that in first and then to solve for C, like before simplifying?
Yes. And so let me maybe try to repeat what you asked in my own words, just to make sure that I understand, and also maybe for anyone else out there listening. So after you integrate a separable differential equation, you have two things that you need to accomplish. One is maybe you need to solve for your C value for those initial value problems, right? Where you're given some condition like Y of 0 equals 1 or something like this. So you need to do that, and you need to solve Y equals. And what I felt was your underlying question is, does the order in those things matter, right? Can you solve for C first and then Y, or do you have to solve for Y first and then C, right? Is there a particular order?
Yeah.
And the answer is those things are independent. You can solve for C first, right? And find out exactly what the value is and then solve for Y, or you can do it vice versa. And either way, so long as you're careful and you don't make some algebraic misstep, you can do it both of those correctly.
Okay. And then I have a quick question. Like for one of the WebWork problems, it was like Y of 0 equals -8.
Okay.
And like my friend told me that you have to put the negative in front of like the whole like thing. Why is that? Like my answer would be like square root of like X minus 64 or something, but I get that wrong.
Well, remember, when you take a square root on both sides, right, it's plus or minus, right? So you can either have the positive square root, in which case you could say, if you have the positive square root, when does this intersect -8, right? -8's way down here. When does that intersect? You'd say, well, it doesn't, right? But if you have plus or minus, you're allowed to have either the positive square root or the negative square root. Now the negative square root does intersect -8. right? And so it's not so much that you want to, somehow pull a negative out of the air and give it to your function. It's that you want to choose the negative square root, because that's the one that actually intersects with -8.
All right, for sure. Thank you.
Yeah, no problem. All right, Chris, you're up.
Yeah, so I have some questions, so like on the quiz today, like I have to have two questions, like what can we expect on our quiz to show up today?
Well, first of all, I think you're making everyone worried, right? Yeah, quiz is tomorrow.
I mean tomorrow, that's fine.
Yeah, so the quiz is tomorrow. And I mean, the big thing is that, you should expect something about 6.2 through 6.4. So we learned how to take derivatives and integrals of, exponential functions and logarithms. And remember, 6.4 is kind of a direct upgrade of 6.2 and 6.3. So to some extent, you can kind of, these kind of are all grouped together by 6.4. So I would expect that there's maybe some derivative or integral question about exponentials or logarithms. In particular, like 6.4, again, would kind of cover 6.2 and 6.3. I would expect that, if we wanted to test 6.5, right? Again, this is kind of very algebra heavy, but it is formally a part of our course, right? So, I mean, I would review the Webwork questions there. I suppose we could make a multiple choice, but it seems like a lot of those lend themselves well to plugging in a number, right? It's kind of like one of these things where you have bacteria growing, originally we have 50 bacteria. How long until you have, 300 bacteria? It seems like, that number is an easy thing to plug in. And then for separable differential equations, those ones are a little bit more difficult. Those ones may be a multiple choice as far as right, once you solve your separable differential equation, what the y equals is, or we could ask you to plug in a specific value, right? So once you have that function, we could ask you to plug in, y equals 5 or y equals 2 or y equals 0 or whatever. And you would get some number out for that. But so that's a way that I, would be reasonable to test the 6.2 through 6.4 stuff, the 6.5, and the 9.3, the separable differential equation stuff.
Okay, and yeah, I was just and I had another question. So so about these problems, like right now we are right now we are using U substitution, but when can we learn the shortcuts easily, like besides U substitution? Because there has to be like like a shortcut, because so far we are using that tool in our trick, tricks of the trade. So so when will we actually start using those shortcuts, like like what chapter will come in? Or
I'm sorry to tell you, there's no shortcuts to this. There's no shortcuts to the U substitution. It's kind of like, if you're solving the crossword puzzle, in the paper or whatnot. And yeah, when do we get to learn the shortcuts for solving a crossword puzzle? Sometimes it's just complicated and you have to, math is a lot about problem solving. Yeah, I see one person saying, yeah, U sub is the shortcut. It's a way of rewriting things to make it look easier. But sadly, yeah, there's nothing for the problems that are solved by U sub. This is as good as we're ever going to get as far as being able to solve them fast. Sorry to tell you.
okay.
Yeah.
But we'll get to it later, right?
Well, we'll get to other integration techniques. There are some things that can't be solved
by U substitution.
By U substitution, we need to learn more powerful things to deal with those. Things like partial fractions, things like trig sub, things like integration by parts. Those are all coming up in chapter 7. But there are problems, right? These you kind of have to hold in separate hands. The problems that you can solve, for instance, with integration by parts versus the problems that you can solve with U substitution are not the same problems. If I give you an antiderivative, it's very possible that only one of these methods works. And so it'll be kind of a little bit of again, some problem solving as far as, well, which method should I use? right? Should I be using integration by parts here? Should I be using U substitution? Which one should I be using? So yeah, that's coming up in chapter 7.
Thank you.
Yeah, definitely. No problem. All right. Jakayla, you are up. Go ahead.
Okay, the question I had was from the pre-class videos in example 666. It was just a part of it that I missed a little bit.
So this one right here, the cosine inverse stuff?
Yeah, so I just got confused. Okay, the first part was from the cosine inverse, obviously, and then the 5x because that was the inside. But what about the natural log of 5?
So that comes from our rule when you want to take the derivative of a to the x. You get a copy of itself times the natural log of the base.
So that still applies even though that's the inside of that function?
Yep. So this right here would be the derivative of 5 to the x. All of it would be the derivative of 5 to the x. So you need to multiply the cosine inverse stuff with the derivative of the inside and all of it.
Okay, thank you.
Yeah, no problem. Sydney, you're up next.
Hi, I had a question on the pre-class video notes too.
Yeah.
Example 6.12. I was just kind of confused where we got like the 1/2 and the u over 2.
The 1/2 and the u over 2.
After we did the 1/4 integral for the 1 over u squared plus 1.
So yeah, there's two different ways. Since this came right after we developed a formula for this, right? We can just use this formula. So that's one way, maybe the fast way to some extent of doing this would be just, well, we know how to integrate this 1 over x squared plus, well, 4 would be the same thing as 2 squared. So a is 2 in this case. And so you could just plug in the results and right, you would have 1 divided by a is 2, tangent inverse of x over 2 plus c. And I guess technically we're using a u substitution, so our integral would have a u here. So that's one way. I mean, the other way is we would follow all of these same steps, right, in order to come up with the result. So that is, we would do a rewrite. We would divide by 4 on top and on bottom in order to get a perfect square here plus 1. And then that would fit our formula for tangent inverse. We would do a u substitution. Then we would do our antiderivative and substitute back in instead of u, right? We would substitute in x over 2. So
oh, okay. Thank you.
Again, it's the same steps as we did in the last problem, but now with kind of a specific number.
Thank you so much.
Yeah, of course. All right. Let's see. Bashad, you're up.
Unfortunately, my other class starts in 1 minute, so I have to go.
Fair enough. Post your question on Piazza or come to office hours at 4. No, wait, not today. Tuesdays, Wednesdays, and Fridays at 4 o'clock. I'd be happy to answer it.
Sounds good. Thank you.
Yep, no problem. Tyler, you're up.
Yeah, so I was just looking at like the first couple web work questions.
Yeah.
And I saw it's like a lot of like, what is the